Okay, welcome back to Engineering 255 Statics. This is the second video of the chapter 10. We're going to continue the discussion about the moment of inertia of an area. We're going to introduce a very important theory. It's called the parallel axis theory. And then we're going to introduce an idea called the radius of gyration, which is a measure how far the area is away from the rotation axis. And the next idea that we will talk about is that if you have a complicated shape, we can use a similar thing that you learned in the previous chapter to find the moment of inertia of the overall things by separate the complicated parts into a smaller pieces. So let's dive in. Okay, so the objectives that is that after this video, you're supposed to know how to apply the parallel axis theory. And the second thing is that we're going to show you how to find the moment of inertia, or the MOI, of a composite area. Let's start with the application. Now, if you look at the picture, there's a T shape of a column right here. If you look at the book, then we have like a simple shape, and you can use the integration to find the moment of inertia. But for this kind of shape, it's really hard to find because the shape that you have is discontinuous. Doesn't matter that you go across horizontal or you go vertical, you're always going to have some discontinuity, right? So and when you look at this one, then how do you determine how much of a moment inertia? You have to find an axis. So we wanted to find a simple way to determine the moment inertia for this kind of shape that is not a simple like a circular or rectangular. Another example, which is this one here, this is more complicated. You can see there's smaller pieces in this picture. And we can use the idea of the composite parts to find the moment of inertia for the whole things. So we're going to show you how to do that. Now let's start with the parallel axis theory for an area. Now suppose that you have an arbitrary shape. So this is the shape of an object. We want to find out if this one is going to rotate, and how do we find out the moment of inertia of the area? And this is corresponding to an axis. Okay, so if you look at the x-axis, then everything will be turning around the x-axis. If you look at y, then everything will turn around the y. So this just kind of tells you if you have a load that's go this way, and then you are likely to find out the moment inertia with respect to the y-axis. If you have load go horizontal, and this will be determine the moment of inertia in another axis. So it depends on the load, right? And so we want to find out, well, in which way that you have a larger or smaller moment of inertia. So you have to look at how far the object is away from the axis, because it will create a different amount of the moment. There's two kind of a moment inertia of the area, and one is just simply the x and y. This is corresponding to the Cartesian coordinate. So if you have a two-dimension like this, you have x-axis and you have a y-axis. And when we do the moment inertia, if you're not rotating about the center of the object, you are rotating about somewhere away from that, then you have to use a parallel axis method. This parallel axis method has to choose the axis which is parallel to your axis of the centroid. And you have to pick the axis. So we're looking at how this one is rotating about the axis that you choose. All right, so let's look at the equation. How do we do that? So if you want to find Ix, which is the moment of inertia of the x of the area with respect to the x-axis, the definition is you do the equation, u times the y squared dA. And this y here represent the y-axis that you choose. The distance of, it should be the distance of the centroid to the x-axis. So say, for example, look at this picture right here. We're looking for the moment of inertia of the area with respect to this x-axis. And the y is going to be defined by any of the position in the shape and how far that is away from this x-axis. That's the y, right? If you have this point here, then your y is simply this distance, which is the y. If you have this point right here, and this is going to be the distance of the y. But you're going to cut it into smaller pieces, and you do this integration like this. But we're going to use, if you have this one here, for example, and they're using this one as an example to show you, let's say this is a dA. This is the area that you try to find and you try to integrate. And the y is equal to this y prime plus the y, which means you can represent the y by using a centroid first, and then you add with the distance of the area away from the centroid. And there's a reason for that, because if you look at the book, there's a table to show you like a simple shape. But all those moment of inertia is with respect to the centroid. They don't give you any of the point, right? Any of the axis away from the centroid. So everything is around the centroid. And if you can find that away from the centroid, and we can use parallel axis to find any of the axes that you are referred to. So I'm not going to go through the detail on this equation right here, and when you do the integration, you kind of expand this part here. That's why you get this one here. And then we can use the definition of the centroid to find this one here. At the end is, this is what we call the parallel axis theory of the area. Now you have Ix, which is the moment of inertia of an area with respect to the x-axis, and it's going to be equal to this one here. So this one is the one that you can find from the table. This is a area moment of the inertia of the area with respect to the centroid of the x-axis. So this is the centroid, this is the x prime. You do the x and y around the centroid point. And you have to add the A. The A represents the total area of the object, which is this one here. And then you multiply the dy squared. The dy is the distance of the centroid to the axis. Okay, centroid to the axis. You have to find the shortest distance. Okay, you can't say, oh, this is going to be distance, or this is going to be distance. No, it's going to be shortest distance from the centroid to the axis that you choose, and that is going to be the square. What is the unit of the moment of inertia? It's the length of power of 4. So area is m squared. This is going to be the m squared as well. So this is n of power of 4. Similarly, you have Iy equal to the moment of inertia with respect to the centroid of the y-axis plus a dx squared. Now, be careful. This is a y prime. This is a dx squared. This is the ix. This is a dy squared. There's another moment of inertia which is called the polar moment inertia. It's going to be equal to the sum of these two. When you do a polar, you don't look at the axis, you look at the point. So in this picture here, the polar moment inertia is with respect to this point origin. And you look at, this is useful when you have a circular shape, okay? If you have a circular shape, you're going to use this one. And this d here is going to be the distance from the origin to your center of the centroid. So to give you a summary of this one here is that if you look at this, kind of show you why this one Ix is equal to this one. This is what we call the centroid of the center of the moment of inertia, and we use Ix plumb to represent that here. If you add with the total area and you multiply with the distance of the axis of the parallel axis, and that will be equal to the moment of inertia. That is this one right here, and this is the parallel axis theory. And again, I also mentioned about the polar moment inertia, which represents as the J. You are looking at a point, not an axis. This is the equation, and this is how it come out to be equal to Ix plus Iy, and simply just R squared equal to X squared plus Y squared. So very simple that you can see this is the definition of the Ix, and this is the definition of Iy. This is one of the table that shows you the moment inertia and the centroid. So if you have circular shape, if you look at centroid, which is right at the center of the circle, you can find Ix, you can find Iy, and that is all equal to this because they are symmetric. But if you want to find the Ix, which is that you refer to this axis, not this axis, okay? So this part here is with respect to the centroid of the circle. This one here represents this one right here. So it will be different, okay? The other one is the polar moment inertia, which is this one, and when you do this one is with respect to this point right here, or yeah, it's going to be this point here. Okay, the next topic we wanted to tell you is the idea of the radius of a gyration of an area. So the idea is that if you look at the entire area and you want to find the distance, use a single measure to see how this area is spread around the axis. Let's say we wanted to see how this area is spread around the x-axis. And you can use this way to find. So when you find Ix, you simply say, okay, I want to find the radius of gyration, and you put the total area at here, and this will be the indicator how far it is away from the axis. Is a kx squared. Again, the reason is this one is length to the force. The radius is kind of a like idea that you have a unit of the meter as well. Meter squared times area squared, yeah, that's going to be the meter to the force power. So kx, the radius of gyration, is going to be square root of the Ix divided by a. If you use y, this will be Iy divided by a. Okay, if you use the polar, and then will be equal to J0 divided by a, that all represent the reference point that you choose. So this is just a measure, give you an idea how spread of the area around the axis. All right, the last topic in this video we want to give you is what happens if you have very complicated shape like this one here. but the shape actually can be treated like a smaller pieces of some kind of a primitive shape, like a triangle right here, rectangular right here, another rectangular which is cut off. Remember what we did in the previous chapter? So we're going to look at, if this is one of the shape, we want to find out the moment of inertia with respect to x-axis or y-axis, or with respect to the centroid. All these things you can calculate, and this is going to be main focus of your next exam. I'm going to use example to show you, but let me just start with a step. It's similar to the previous chapter. First one is that you divide a given area into smaller, a simple shape. So like this one is the example that you have a rectangular with circular inside, but it's a cut off circular. You can treat it as a big rectangular and minus a smaller circle. And if you look at the centroid, then you can find this number from the table. It will give you the Ix and Iy. You can find the Ix of Iy of this one as well. And then you can find the total centroid Ix. But if you're looking at this axis, then you have to use the parallel axis method to find that. So this whole process is kind of tells you. And everything here is just simply just add or subtract number. There's no like a vector. You do algebraic summation. So it's a very simple process. You just need to do some example. So here's one example. We have an I-beam right here. And this I-beam, the top and bottom is the same shape. You have a vertical go through the center. We want to find the moment of inertia of the area about the x-axis and also the radius of gyration. We're going to separate this one into three different shapes. The top one, the middle one, and the bottom one. Right? They are very simple rectangular shape oriented at a different way, but they are just very simple shape. And the centroid is very straightforward. It's going to be just right at the center of the shape because the shape is very simple. And the distance of the top and bottom away from the centroid is going to be able to find from this information that is given. So if you look at here, this is a 300 millimeter. So from the center to the bottom of this vertical bar is going to be 150. But the distance is not going to be 150 because this bottom part also have a thickness of a 50 millimeter. So half of that is 25 millimeter. 150 plus 25 is going to be 175. That's why you see this 175 millimeter right here. The reason that we need that is that we need to know how far that is away from the x-axis. So now you have three different parts. We're going to use the parallel axis theory to find that. If you look at the table for rectangular, this is a very common shape, so you probably will need to know how this equation is. This is the equation to find the moment of inertia for a rectangular shape. It's 1 over 12 times b h cube. Okay, so this b is going to be the base, the h is going to be the height. If you look at a shape of 3, this is a shape of 3. Okay, the b will be 200 millimeter, the height will be 50 millimeter, and you have 1 over 12. This number is the center of the moment of inertia around this center point of this part here. So it is around this axis, and which is this one here. What Well, the same thing if you do the part 2. When you do part 2 here, your base become the thickness of this, which is 50, and the height become 300. That's why you have a base h cube. And you will see these two are quite different, right? This one is going to give you 1.125 times 10 to the 8. This one give you 3.083 times 10 to the 8. Okay, they are all to the 10 to the power of a, but the value is going to be, this one is almost like 3 times larger than this one here. So the orientation of the shape make a big difference. So how do you find the total? Well, very simple. You just add the shape all together. We just find out the ix1 and also the ix2, which is the top shape, middle shape, and the bottom shape, right? These two are going to be the same, and this one is the middle part. You sum all the value together, you got a total, and this is going to be the total moment of inertia. And in this case, we're looking at x-axis, which is right at the centroid, and that is great. Then we can find the radius of gyration. When you find this one, you want to find the radius of gyration. You take a square root of ix divided by the total area. The total area is going to be the area of all these three parts together. Okay, and we find this kx is 144 millimeter.